Welcome to The Explainer. We're here to take some pretty complex research and turn it into something clear, something you can really sink your teeth into.
So let's talk about the central paradox of artificial intelligence, right? On one hand, its progress feels just unstoppable. But on the other, the entire field of computer science is built on very real, very hard limits. How can both of these things be true at the same time? Well, that's what we're going to unpack today by building a unified theory to explain it.
Okay, so to really get this, we have to start by looking at the deep, theoretical foundations of what a computer can even do. This isn't just about making faster chips. This is about the fundamental logic of what is and is not solvable.
And this quote right here, it gets to the core of it. The idea is that intelligence isn't some final destination we're racing towards. Nope. It's actually a process of constantly moving up. Every single time we automate a task, we just create a new, more complicated task of managing that new automation.
This brings us to the first key concept, step mechanization. The easiest way to think about it is like this. Intelligence is an infinite ladder. You can't just jump to the top. The way we make progress is by building one rung at a time, mechanizing one layer of problems, which then, poof, lets us see the next rung, just waiting for us above.
And this slide just visualizes that cycle perfectly. You see each layer, let's call one AN, represents our current capabilities. And it has a hard boundary, problems it just can't solve. But when we take that next step and we mechanize a new process, we create a stronger, better layer, AN+1. But here's the kicker. That new, more powerful layer, it has its own new boundary. The ladder you see is truly endless.
Okay, so we've got to be clear, there are two types of limits we're fighting against here. On one side, you have the uncomputable. These are the absolute theoretical brick walls, the top of that infinite ladder. Then, on the other side, you have the intractable. These are problems that are solvable in theory, but in practice would take something like the lifetime of the universe to actually compute. And that is the practical limit that AI is wrestling with every single day.
And that brings us to this idea of staged, bounded ascent. This is basically our strategy for making progress against those practical, intractable limits. We're not breaking any fundamental laws of computation. What we're doing is cleverly expanding the zone of what's feasible. We're turning what used to be a really difficult external search problem into just a single manageable step inside a bigger, smarter, but still limited system. This is the formal foundation of our whole theory.
All right, so we've got the formal theory of this infinite ladder. But how does this climbing actually happen? In the real world, what's the engine that's actually pushing AI up this ladder of progress?
Well, the answer turns out to be something you've probably heard a lot about, the incredibly powerful and, honestly, surprisingly predictable phenomenon of AI scaling laws. The basic idea that if you just add more data and more compute, the models just get better in a very, very predictable way.
Now, to really understand these scaling laws, we have to make a key distinction between logical compute, that's the abstract mathematical work being done inside the model, and the actual physical cost in watts or dollars that it takes to do that work. Scaling laws, you see, operate on that logical level.
And this graph shows the secret engine at work. It's not just about throwing more money at the problem. Look at those curves showing how the error rate drops. Progress depends, critically, on the rate of efficiency doubling. The black line, the one with faster doubling, gets to a much lower error rate, way faster. This compounding efficiency is what makes it economically possible to afford the next more expensive step up the ladder.
So the bottom line is this. Efficiency is the fuel. It's all the innovation we see in algorithms, in software, in hardware. That's what allows us to keep climbing that ladder even when every new rung requires, say, 10 times more logical compute than the last one.
And this constant, relentless pressure to scale and get more efficient, it doesn't just live in the world of software. It fundamentally reshapes the physical machines, the hardware that we build to run AI.
To see how this works, we need a concept called the value scalable fraction. Now, it sounds a little technical, but it's actually super simple. It's just the percentage of a task, say generating an image, that actually gets better when you throw more computing power at it. It's the part of the job where scaling still creates real, meaningful value.
This little formula here might look simple, but it is incredibly powerful. RC here tells you how much more efficient a specialized custom-built chip needs to even be worth making, and its value depends entirely on S, that value scalable fraction we just talked about. And as we're about to see, that relationship is, well, it's pretty explosive.
This race diagram brings that formula to life.
Okay, so on the bottom axis you have S, the scalable part of the workload. Now watch what happens. As S increases, as we make more and more of our AI models scalable, look at how that blue line, the efficiency you need, just shoots up exponentially. This creates this huge red collapse region where building a custom specialized chip just doesn't make any sense anymore. It becomes way better to just use flexible, programmable hardware.
And the result of this explains so much of what's happening in the tech world today. It's exactly why GPUs keep getting more and more programmable. It's why the best AI accelerators have to be general enough to not become obsolete in 6 months. The constant search for the next rung on the ladder is physically pushing our computers away from rigid, specialized designs and towards flexible systems that can adapt to wherever the AI frontier moves next.
Okay, so let's tie this all together now. We've got all the pieces on the board, and we can finally assemble them into one single, coherent story of AI progress, a story that connects the deepest theories of computation directly to the actual silicon sitting in our data centers.
So here it is, the whole research program in 4 parts. The first 2 points that give us that formal, theoretical foundation, this infinite ladder that we climb with these clever, bounded steps. And the next 2 points, that's the empirical and architectural bridge to reality, the engine of scaling laws and efficiency that physically reshapes our hardware. You see, it all connects. And what this framework really gives us is a whole new way to think about things. The very same science that taught us about hard limits and unbreakable boundaries can be flipped right on its head to become a language for actually understanding and maybe even predicting the path of progress itself.
So the crucial takeaway here isn't just a neat story about how we got here. It is a powerful framework for thinking about what comes next. It explains the relentless, yet structured way that AI advances, and it leaves us with this final, really provocative question. We can see the rungs of the ladder we've already climbed, but what does the next one, the one we're building right now, actually look like?